This work is under the supervision of Dr. Marian Bomadi-Lopez from Basque University and Professor Bizhen Chen. And it's basically based on these two published papers. The later one, which was published last year, was also with collaboration with Marian's student, Emmanuel Alvaran. So let's begin. So we know that Einstein gravity is a very successful theory, but it still has some fundamental problems. For example, the singularity problems and the current acceleration of expansion is still with us. There's still no proper explanation of that. So to explain the acceleration, some people may resort to introducing some kinds of dark energy, for example, the cosmological constant, or some dynamical dark energy, such as quintessence or even phantom dark energy. But we need to notice that the introduction of phantom dark energy may also lead to some or more cosmological singularities. So here I list some of the famous cosmological singularities. The first one, Big Bang, we are all very familiar with that. So it essentially corresponds to some divergences of space-time at the zero size of the universe. And the other three, the big rib, and little sibling of the big rib, are generic doomsday, future doomsday of a universe of phantom-dominated space-time. And in these three scenarios, the energy density of the dark energy will increase with the expansion of the universe. So, oh, okay. Thank you. So at some certain time, for example, when the scale factor, the size of the universe goes to infinity, the Hubble rate and the sum of the scalar invariance of the space-time will also grow up. Furthermore, all of the bond structure, for example, like the galaxies, atoms, or whatever, will also be ripped apart before this cosmological singularity, these three. So to resolve the space-time singularity problem, there have been many literatures trying to formulate some extended theories of gravity on top of the Einstein gravity. For example, in 2010, Baniados and Faria, they proposed the so-called Eddington-inspired-Born-Infeld gravity. And this theory, you can see from this action, is characterized by the square root structure in this action. So because of this square root, you can imagine that the curvature will naturally have some upper bound. So instead of blowing up, you will bound it from above. So this idea is essentially inspired from the Born-Infeld electrodynamics, which was proposed in 1934. So because of this square root structure, this theory will behave very differently from Einstein gravity when the curvature term is very large. But the good thing is that it will recover Einstein gravity with a cosmological constant when curvature is small. So it has a proper limit. Then because of this significant difference, the Big Bang singularity has already been proven that it can be avoided in this model. So for example, you can see this picture. So this picture, I will demonstrate how the Big Bang singularity can be avoided. So if we trace back toward in time, then you can see that the size of the universe, instead of going to zero, it will have some minimum size. So the Big Bang singularity can be replaced with either initial state with this minimum size, or it can also be replaced with a bouncing solution, depending on the parameter in this model. So given that the Big Bang singularity can be avoided in this model, it is quite natural to ask whether the big rib or little sibling of the little big rib singularity can be avoided as well or not. So in our previous works, we have already done this. We studied the phantom dark energy model in this theory, and we proved that these three types of singularity are still unavoidable in the EIBI model. Okay? So everything here are classical. So here I will also demonstrate how the bond structure will be ripped apart near this singularity. So imagine initially there is a bond structure with a circular orbit initially. Then with the expansion of the universe, the Hubble flow will become stronger and stronger. So this system will be acted by some repulsive force due to the Hubble flow, and in the end the radius will increase. And near the singularity, you can see that this system will be taken away from this Hubble flow. So that's why we have the notion called rip in this type of singularity. So we know that these cosmological singularities are still unavoidable in the EIBI model. So we know that the theory is still not complete. So some quantum effects should come into play. And in the literatures, there have been some references in which the authors study the quantum avoidance of these singularities in the context of Einstein gravity. And it has been proven that these singularities can be avoided. And so it is natural to ask whether we can find a similar quantum avoidance of these singularities in this model. So that's one of the motivation. So how do we do this? So we at the beginning we assume a Freeman momentum Robertson Walker ansatz because we are interested in the cosmological singularity, the cosmological scale. And we use the so-called quantum geometrical dynamics in which we want to construct the Hilbert equation, which can be used to describe the quantum behavior of the whole universe. And to justify whether the singularities can be avoided, we use the so-called DeWitt boundary condition. So in the end of calculation, we want to see whether the solution of this Hilbert equation vanishes near the cosmological singularity. Then if it vanishes, then we will argue that the probability of the universe to approach this singularity may also vanish. So we use this to argue that the singularity may be avoided in this model if the wave function vanishes. Okay, so that's the idea. So in the following slides, there are some details. So in principle, I will go through it faster. So we start from rewriting the original EIBI action into its Einstein frame. And the advantage of this is that this action is more similar to the Einstein-Hilbert action, and using this action to derive the Hamiltonian and so on is much easier. Okay. So we assume, as I said, we assume a Freeman momentum Robertson Walker ansatz. So we have metric. We have left function of the metric and scale factor. And the reason why we have two matrices in this model is because of the affine structure in this theory. It's too detailed, so I will not go through this. So what we do is simply put all these ansatz into this action. Then we can have the Lagrangian here. Then we calculate the conjugate momenta of this system, and we see that this system is essentially a constraint system. So some of the conjugate momenta will lead to the existence of primary constraints. So in the end, we can see that we have three primary constraints in this model. And we can also construct the total Hamiltonian. Then the conservation in time of the primary constraints would lead to the secondary constraint. So we have 6 secondary constraints here. Then so we have so many constraints, and next we need to identify which of them are first-class constraint and second-class constraint. This is very important because we will construct the correct Hamiltonian to construct the Hilbert equation. So in the end, we find that in these 6 constraints, there are 2 first-class constraints. The first one corresponds to the gauge degree of freedom, and we can always fix the gauge by choosing some assumption. And then the other first-class constraint is the Hamiltonian itself. So the Hamiltonian itself is a first-class constraint, and we will use this fact to construct the Hilbert equation. So that's the idea. And the other constraints we have so many parameters, so many constraints, so they are just second class, and we will use the Dirac bracket to promote the classical system to quantum operators. Okay. So here are just the definition of the Dirac bracket. So the advantage of using Dirac bracket is that all of the second class constraints, after promoting them to quantum operator, we can treat them as zero operators in the quantum level. So it means that in the final expression of the Avoidance equation, we can use these identities to simplify this final expression. So in the end of the story, we have a final Avoidance equation, and it is essentially a single variable differential equation. Then it's very easier to solve it. So near the singularities, we can assume that the scale factor goes to infinity, and then we can solve the differential equation to derive the asymptotic solutions. So we have the wave function here, and as you can see, they are just some kinds of Bessel functions. Then when the scale factor goes to infinity, the wave function, as shown here, indeed vanishes. So it satisfies the boundary, the weak boundary condition. And here we use the second factor ordering. It is just more or less the same thing. We write the Avoidance equation and we solve it, and we prove that the weak boundary condition is still satisfied in this second factor ordering. Okay. So here is the conclusion. So in this work, we have shown that the big rib, little rib, and little sibling of the big rib are still unavoidable in the EIBI model, and the bond structure will be ripped apart near these singularities. So we use the quantum geometrical dynamics within the EIBI framework, and we perform all of the constraint analysis, and we derive the proper Hamiltonian, and use this Hamiltonian to construct the Avoidance equation, and we solve it. We solve it based on two-factor orderings. Then we find that the weak boundary conditions are indeed satisfied. So we claim that the classical singularities here can be avoided by some quantum effects in this model. So that's basically this talk. So thank you very much.